Okay, so good afternoon, everyone. My name is Valentina Marticorena, and with my colleague Leo Su, we're going to be presenting research that we developed in the Design Research Laboratory here in London, a postgraduate program. And our director was Dr. Theoros Peropoulos. And the studio basically challenged us to think natural phenomena as a form of technology. And within that framework, our team was really trying to explore how we could conceive a space that is in continuous formation by harnessing the hidden forces that structure basically everything that is around us. And by engaging and manipulating those hidden forces, what we were able to do is kind of like learn how to influence how matter behaves and to be able to recognize legible and legible spatial patterns that basically evolve over time. And the scope of this presentation is going to be the research question, which is what are the potentials of a space that is conceived beyond the fixed and finite? And the attempt to explore that question, which was by integrating the analog experimentation and computational simulation in order for us to translate natural phenomena, and more specifically quantum phenomena, into a space that can be more ephemeral, more durational, and participatory. This is a summary of our methodology. We're basically starting from a very fundamental understanding of energy and matter. We really run through this very iterative dialogue between physical prototypes and computational simulation, and each of the prototypes inform the next step of development. And I think that the evolution went through, let's say, more of an understanding and observation kind of attempt in order to try to organize this phenomena to much more control and influence. And for this part of the presentation, we're going to be looking at more of the analog prototyping, where the key phenomenon that we observed is a hydrodynamic quantum analog called bouncing droplets. And it's a non-coalescence phenomenon that happens when we create a droplet from a vertically vibrated silicon oil bath. And what happens is basically when the droplet is pulled downwards by gravity, there is a layer of air between the silicon oil bath and the droplet that gets compressed and then propels the droplet upwards. And this is a system that regenerates in each of the impacts. So it basically stays on a loop, bouncing on loop. And something very interesting is like the droplet and the wave become inseparable. And what we found very fascinating from the more spatial and architectural point of view is how these particles start to organize in very intricate self-organizing patterns. And it's basically because of this interaction of the wave field and interference between not only the droplet with its own wave, but the droplet with the wave of other particles. And something also very relevant about this quantum analog is that it's mirroring a phenomenon that happens at the subatomic level. And even if it's very small, with this droplet is 1 millimeter of diameter, the jumping scale is actually very big. So for us, it's just not like a simple analog, but actually a demonstration that these logics of organization are actually relational and that we can observe them at different scales. So to be able to replicate and to actually be able to observe these organizations, we had to create our own custom setups. In this case, we had the silicon oil bath in a petri dish. This was kind of a very controlled environment. So it's a leveled platform with some accelerometers to see that we didn't have any vibration variations. And also we had an on-demand piezoelectric dropper to be able to deliver the droplets in a much more smooth way into the bath. And just to summarize some of the key parameters and behaviors of the droplets, the first variable that I think is one of the most important in the system is frequency. In this case, it's a sound-generated mechanical vibration. And the frequencies that we were working with varied between 40 hertz and 140 hertz. And there are two key behaviors of the droplet. One is the stationary bouncing that happens when the droplet is aligned with the center of its own wave. Or we can have a walking behavior that happens when the droplet is a bit off center with the center of its wave. That means that when it's going to impact, it impacts in the slope, and that propels it to walk forward. And another very interesting aspect of this wave field is that there is a residual wave field from the previous impacts of the droplet that kind of keeps affecting the droplet's current position. So the droplet is not only guided by its own wave, but actually it's interfering with its path trajectories. And there are two organizational logics that we identified with lower frequencies. We can recognize much more stable formations and droplets being locked with their interference for much more time. Whereas when we are having higher frequencies, we kind of observe much more chaotic behavior of the droplet, and they tend to be organizing in more packing systems. And this is a digital catalog, actually, of many of the organizations that we could observe in our physical prototype, from individual behaviors to collective ones, and all the richness and information that was captured in the wave field of the droplets.
Thank you, Ali. Now we'll move on to the computational simulation and implementation part of the project. So along with the physical part, we also built a simulator of the bouncing droplet phenomenon using a mathematical model from an academic paper published by Dr. John Bush and his research group at MIT. So the learning curve of implementing this mathematical model was twofold. First, understanding specifically what the equations were describing, and also finding a way to implement it in Houdini. So the mathematical model can be broken down into three parts. First, the vertical dynamics of the droplet. So the equation on the right is essentially describing the vertical acceleration of the droplet, how we need to consider the gravitational force when the droplet is in the air, and also the normal force or the impact force when it contacts the fluid surface. The horizontal dynamics or the horizontal trajectory of the droplet is the X and Y direction that the droplet moves in. And essentially the equation describes how we also have to take into account the impact force and the gradient at the impact point in the X and Y direction. And the wave model, or the kind of wave formation underneath the droplet, is calculated by kind of conceptualizing the surface as a field or grid of points. And each point is calculated simultaneously with the other points and recalculated at every frame. And it takes into account physical properties such as viscosity, the forcing amplitude and frequency, and also the contribution from previous impacts. And it also takes into account this distance from the impact point and also the time that has passed since impact. And one key kind of aspect that we realized when we're trying to implement the mathematical equations is that terms within the equations itself would have more terms, have equations that define those terms, and those equations would have terms that have other equations, such as this amplitude term at the bottom here. And these were some of the physical properties that were kind of acted as input into the system. So things such as material property, including surface tension, fluid density, and droplet radius, and environmental factors, and forcing frequency, forcing amplitude, and also fitting parameters that were defined in the paper to be a specific value in which the other researchers have fine-tuned to kind of match the digital simulation to the accurate physical behavior. And in our simulations, we actually played around with a multiplier on the wave height value to kind of to be able to iterate and kind of test different things a bit faster rather than waiting for 100 bounces or a longer simulation time to see those self-organizational behaviors. And this is a kind of the implementation structure of the different equations. So we can see the vertical dynamics, the wave model, and the horizontal dynamics equation at the bottom. And essentially it's made up of these terms that's implemented before them. So at the top, we have the physical parameters that we saw before. And one key feature of this mathematical model is that it's non-dimensionalized. So it's a generalized model. And what that means is that rather than having real physical units, it's all the terms actually defined as a ratio within these equations. And one way of thinking about it is in a recipe, it's kind of saying like having 2 parts flour, 1 part water, rather than specifically saying there's 200 grams of flour and 100 grams of water. So an example of this is a dimensionless vibrational acceleration here, where it's pretty much saying the vibrational force is in proportion to gravity acceleration or gravity force. So these kind of derived quantities kind of are like the building blocks for the final equations, and they make up the equation for the droplet impact force and also the wave model terms to the right. And once we have the vertical dynamics and the wave model, we feed it into the horizontal dynamics. And for the kind of the gradient and the impact force. And the final output, we actually have the droplet motion and the wave formation, which act as the input for the next frame of calculations. So the output, after implementing the mathematical model, we could kind of index it in different ways and kind of visualize the trails and watch the droplet bounce around in the simulation. And we also implemented the wave interference of the different droplets so that we could see the self-organizational behaviors that we saw in the physical experiments. And one of the first things that we realized was that in the simulation that different droplets can occupy the same wave, and kind of the size of the wave is dependent on how many droplets is within that wave. And there can be too many droplets in one wave. So when the wave becomes way too steep, the droplets would kind of explode out and reorganize. And when they're reorganizing, they actually reorganize into these dynamically stable formations, like we saw in the physical experiments. So they organize into these stable triangular lattice formations, as we can see. And one key point in instrumentalizing the simulation was that we shifted our focus from this iterative testing of the droplet kind of positioning to the wave field itself and visualizing the wave field not only in 2D, but also in 3D. And one further step was that we realized that we could actually implement an agent with a choreographed movement to kind of trigger this transformation between 3-dimensional wave fields. And this is a initial testing of the possibility of actually having these choreographed interactions between an agent who moves at the right speed and could actually move these a collective group of droplets in one direction. And this is kind of assigning also a different type of waveform to the droplets and the agent. And this is another example where it's kind of utilizing that triangular stable formation to push another droplet forward. And again, assigning a different formation, kind of a wave, different size waveform to the droplet and agent to create this kind of recursive 3-dimensional form. And in spatializing, so this kind of molecular phenomenon into a human scale, we can envision a system where the bouncing droplet algorithm kind of informs the interactive self-organizing system. And the people in the material landscape is kind of the location data is sensed through a field of sensors and fed into this algorithmic system. And also the transducers then kind of respond and create this feedback loop between the material environment and this algorithmic world. So eventually we can have a material environment that's in continuous formation of a non-Newtonian material.
And in trying to prove this concept of integrating the human in the system, we developed another physical prototype, which was a much bigger scale, which also implied us to change the material from silicon oil to water. And we also wanted to experiment what it would be like to have different sources of vibration, just to try to represent that larger landscape. And for that, we placed 7 transducers, a membrane that was vertically vibrated by those transducers, and also 7 ultrasonic sensors. We mapped the distance of the sensors to different frequencies, and we also created our own custom-made PCB boards that were basically getting the data from the sensors, processing it, also creating its own frequency, and then amplifying it and sending it to the transducer. So what we were able to do with this prototype was basically improving actually this concept that we could get environmental inputs, so in this case, the proximity to the hand, in order to be able to start to visualize how this input can start to form this wave-filled landscape. And something that was very crucial about this prototype, like scaled-up prototype, was the ability for us to see how the different frequencies start to interfere and kind of fragment this landscape, and kind of like starting to suggest the different possibilities of running the algorithm in different scales. And we do understand that there is a limitation, not so much with the material itself, but actually on how humans engage with matter. And we try to bridge that gap by trying some VR tools and just to see what it would be like to be in a space that transforms and have like this wave-filled organizational logic. But we also think that these limitations can be taken actually as very productive thresholds, where invite us to really think what are the future possibilities of a space that is in continuous formation, and what are going to be the implications for us to really achieve a space like that. And we do think that the space that is transformative actually aligns with the world that is in constant motion. So actually, from moving from this understanding of humans as passively observers, but actually bring them into the system as actively shapers of this collective environment. And we like to see this as a continuously evolving field of inquiry. And we think that our research remains open-ended. And what we're trying to show is more of an attempt to see how these digital and physical tools, and also a very fundamental understanding of matter and energy, can help us to start speculating what it would be like to experience a space that is participatory, durational, and formational. With that, thank you so much for your attention.